So, good evening, everyone. Welcome to CS 106K's assignment 3. And the first question required me to answer about least squares fitting of a plane. And it required me to generate 500 points with additive Gaussian noise. And that is what I do here. So I basically I pass these two parameters. So n is equals to 500 for 500 points and the standard deviation for the Gaussian white noise. And eventually I get an output for 500 points. And then the next thing I do is I will use the normal equation from linear algebra to find the parameters for the point. So I need to find alpha, beta, and gamma. And so what I do is I create the matrix A using the value of x, the value of y, and this constant at the end, because in the equation that part is also 1. And then I use the z value here, z value as my b, and then I implement the formula, and eventually I get the parameters that were estimated. And the last part is to print to the screen the absolute error you found between each parameter of the ground truth and the estimated plane. So I just do like what I'd set up here minus the values that I got after running the formula. If I run this code, I get there we go. So the absolute error for alpha was this, for gamma, for beta it was this, and for gamma it was this. Now, the next question was about optical flow. And a very brief thing about optical flow is that it refers to the pattern of apparent motion of objects, surfaces, and edges in a visual scene caused by the relative motion between like an observer and the scene. And so if you have like two images of the same scene taken at slightly different times, the optical flow gives you a vector field indicating how each pixel in the image has moved from one frame to the next. And most of the times, my implementation uses the Lucas-Canid method. And the assumptions of the Lucas-Canid method are like constant brightness, small motion, and that neighboring pixels typically move similarly. And for one other thing is like in my code, I implemented a pyramid because for the third set of images, the corridors, there was a big shift and from image one to image two. And basically, as one of the assumptions for Lucas-Canid algorithm is that there is this small motion. So the pixel displacement is small relative to the image resolution. But between those two images, it is a lot. So by using a pyramid, I get to show that flow. Like I get a proper flow rather than a messed up flow. And and yeah, so in this code, I start by loading and normalizing the images, and then I build the Gaussian pyramids. And so then eventually, once I reach the myflow function, I build the pyramids, I set the derivative filter. I like build the pyramids, the warp things. Then I find all the spatial derivatives, the temporal derivatives. I compute the products, and then I sum all of them, all the values up. Then I run a nested for loop to generate the matrix M and B for each pixel, each point. And if the eigenvalues for that point are more than the threshold, then that point is considered like an interest point, and I can use that to calculate flow. And anyway, after running all the calculations, I'm returned back with U, V, and binary map. So U is like direction in x-axis, V is direction in y-axis, and then like binary map is where all the like where the optical flow is happening. So then I plot the flows on my images, and then there's also the my warp function for the third part of the question. And I can visualize the difference between like in the warp, between the original image and the warped image. And that's what I do for the corridor, the synth, and the spheres. So now I'll just run my code and it's running, waiting for it to run. There we go. So this is the optical flow visualization for the corridor. As you can see, like the images are moving to the right that. And this is the absolute difference, which is good. We expect this. And you can see like the warped image and the original image like very close to each other. And now this is for the synth. Again, the absolute difference is like black, so like it's good. And you can also see like the warped image and the original image are very close to each other. And the last part will be for the sphere. It should be up here any moment. So you can see the sphere is rotating to the right like that. And the optical flow, most of it is happening in the center. And again, you can see absolute difference is very nice. Like it's almost black in the center there. And you can see the warped image and the original very close to each other. So yeah, my implementation works. And thank you very much.